Welcome back. So I'm going to continue the discussion about hybridization. And last lecture, we went through sp3, sp2, and sp hybridization. And I said, if it's sp3 hybridization, expected geometry will be tetrahedral and expected bond angle 109. But if we switch to sp2, and sp2, the geometry, we expect it to be trigonal planar, and the bond angle between the red atom, central atom, and another red atom, that's going to be 120, or yellow and red one plus the central atom, again, is going to be 120. But if you switch to sp hybridization, geometry, it will be completely linear, and the bond angle, it will be 180. And this is one example of tetrahedral geometry. So if you connect the three atoms that here we have inside the base, we get one phase. Okay, that's one phase. Next, and if you connect them to the top one, the purple or blue, any color that you see, and that's gonna give you a pyramid. And each pyramid, it has 1, 2, 3, and at the bottom also we have another face. We have 4 faces for any any tetrahedral geometry or any technically a pyramid. The expected bond angle when it's a perfect tetrahedral, this bond angle is bigger than 90 degree, but it's less than 120, and the bond angle is going to be around 109. Okay, so we're gonna go a bit more in depth about the types of, the bonds that we are dealing with them whenever we have sp, sp2, or sp3 hybridization. Okay, so one example was the C2H4, and we went through this in last lecture. As you see, the bond angle here, we get it around 120. It doesn't matter really which bond angle you're talking about. And carbon, each carbon made 3 sigma bonds and 1 pi bond. Okay, so always the first bond is going to be sigma, and if you make it double, it will be pi. The third one, or triple bonds, the third one, it will be pi as well. Okay, and in organic chemistry, you're going to be dealing with single, double, or triple bond, and with carbon until you make it an octet. Okay, and so I'm going to draw geometry of a couple of molecules and see what we are dealing with. Okay, so the first example, let's say we have C2H6, and this is ethane molecule. Okay, and each carbon is attached to 3 hydrogen atoms, and also attached to another carbon, and that carbon, it has 3 hydrogen atoms as well. So if I label the bonds, I'm going to say we have 3 sigma bonds with hydrogen and 1 sigma bond with carbon. So now any carbon that you pick, it's going to have 4 sigma bonds. Sigma bond. And remember, for each sigma bond, you're using 2 electrons. So if you make 4 sigma bond, means 8 electrons were used to make 4 bonds. Okay, so we use 8 electrons to make 4 bonds. The question is, where do you want to accommodate those 8 electrons? And how do I get the hybridization of, like each carbon? Okay, go with this. Okay, write this one for yourself. Always in any, like from N to, and technically N3, we can say it. And so if N is 1, you're going to have 1s orbital. If n is 2, you will have 2s plus 2p. If n is a 3, you will have 3s plus 3p plus 3d. Okay. Any atom is going to use any orbital that it has access to it, to reach the octet. Okay. Where is carbon? Carbon belongs to the second period, N2. So carbon, it has 2s and 2p as valence orbitals. Okay, as valence orbitals. Okay. For yourself, you're gonna write this. You're gonna write, okay, I have 1s. Always s is gonna be one orbital. Next, you're gonna have 3 from any p orbital. Okay, so p orbital always is gonna be made of 3 boxes. And then you will have 5 from D. D is made of 5 boxes. That means it can accommodate 10 electrons. Question, how many electrons do you have, or how many pairs do you have? I have 4 sigma. Okay, 4 sigma bonds. Okay, so you will say I have 4 sigma bonds, and you just simply you put the 4 somewhere here, and you say equal to. Start using these atomic orbitals. Okay, so I'm gonna call them atomic orbitals. Okay. Atomic orbitals. Start using those until you make it to 4. From S, we can use only 1. And we are still far from 4. How far? By 3. So I need to use this 3 orbitals, 3 more. From where? The lowest, the next lowest energy orbit, next orbital that has lower energy is going to be the 3p orbital. So let's use the 3 from p. 1 plus 3, that's going to give you 4. So you write 4. Next, what did we use? We use S and P. How many from S did we use? From S, we use 1. So you're going to say 1. How many from P did you use? We use 3 of them. So you're going to say 3. Okay, what did I get? I got 4 hybrid orbitals with sp3 hybridization. With sp3 hybridization. Okay, let's practice this one for another molecule. But before I go to next subject, I have to say this, because we got the hybridization is sp3 electron geometry, or expected geometry. Say expected geometry. I got tetrahedral, and the expected bond angle, or theta, expected bond angle or theta is 109.5. Okay, now let's move to such a molecule. We have C2H6. We're going to remove 2 hydrogens from it, and that's going to give us C2H4. So we have a carbon attached to 2 hydrogens, and that carbon, it will be attached to another 2 hydrogens. Okay, remember, carbon has 4 valence electrons, and right now, if you look to any carbon, it doesn't matter which carbon, 1, 2, 3, carbon has 3 electrons there, made sigma, made 3 sigma bonds. So carbon is not acted. And I said, under any condition, you need to make carbon acted. So what's the solution for it? Solution, carbon, because carbon is a group 4, that means it has 4 valence electrons, it's gonna have one orbital on carbon. We call it p orbital, and that p orbital, it will have 1 electron in it. Okay, we're going to call it pz. There is one electron there, it's pointing up, here is pointing up, and those orbitals through space, they're going to find each other and they will have parallel interaction, okay? And that parallel interaction, we're going to call it pi, okay? So this interaction, we're going to call it pi, okay? Let's go dot. That's a pi bond. And I want you to look to the, the p orbital. The p orbital on the top yellow, the bottom one is kind of like pinkish or pink. And so clearly from yellow to pink, we are changing actually sign, okay? Or we're changing color. We say this orbital has a node. And where is the node? The node is somewhere here, okay? Somewhere is here. There is a plane that is chopping the molecule, okay? And chopping technically, the plane, it has actually the molecule in it, carbon attached to another carbon, and two hydrogens are there. But the p orbitals are pointing up and down of this plane. Okay, those are going to be the yellow, so forgive me, yellow one and pink. Okay, so the plane is including the molecule, but is chopping the p orbitals. And we say that plane, we call it node plane. That means it's changing phase of the phase of the orbital. So what's a node? Node is a place or surface that, whenever you pass it, sign of the orbital must change. Okay, sign of the orbital must change. And reminder, we're talking about a wave. Okay, this is positive, negative. Wherever the sign is changing, we say we are dealing with a node. Okay, so now let's talk about hybridization of such a molecule. Okay, so I'm going to pick this. Okay, and now I will highlight one of the carbon. It doesn't matter which carbon. So let's say we are going after this carbon, and I want to know the hybridization for it. Okay, so the carbon that I highlighted, okay, I have 3 sigma bond for it. Okay, yes, I do have one also pi bond. Okay, the pi bond, like I showed there, and this is going to be the pi bond technically. Okay, and is a result of the parallel interaction. Okay, but simply I just say I have 3 sigma bonds. Okay, what's the purpose of the pi bond? Is to make carbon active, but I don't care about it. For now, I'm not going to care about it. Okay, 3 sigma bonds means 6 electrons. I need to accommodate 6 electrons. So I'm going to write this for myself. I have 1 from S. I have 3 from P. And 5 from D. Okay, how many orbitals do I need to accommodate 6 electrons? I need 3 orbitals. How do I know it? Because I made 3 sigma. Okay, now from S, I'm going to use 1. Because max, I have only 1. And from P, how many do I need to reach to 3? Okay, right now we have 1 S. We need 2 more from P to make it to 3. So now you will say 2 from P. And that's going to give us 1 plus 2. We get 3. So we got 3 orbitals, 3 hybrid orbitals. First one is S, the second one is P. From S, we use 1, and from P, we use 2 of them. So we got 3 hybrid, okay, 3 hybrid orbitals with sp2 hybridization. Okay, with sp2 hybridization. Okay, so now let's show those, okay, those hybrid orbitals. You have a carbon with a 3 hybrid orbital. 1, 2, 3. Okay, remember carbon, okay, carbon is a group 4. Okay, so I have another carbon here. Okay, that's sp2, 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 here sp2, sp2, sp2. Okay, in each one, we're gonna put 1 electron. And the second one, they are pointing down, be careful. Okay, and here again, so let me write this one different color. This one is pointing down, but the rest up, up. Okay, you can put them down, it's fine. Okay, you can put those down, but then you need to be careful about hydrogen when you draw. Okay, now these two are going to reach each other and they will have head-to-head interactions. Okay, so I'm going to bring it closer and I'm going to say the interaction between these two, it will be a head-to-head interaction. And I will call this interaction, I'm going to call it sigma interaction. So we got 1 sigma. Next, each carbon is going to have 2 interaction with 2 hydrogens. So the hydrogens, let's show them. The hydrogens are going to be here. Okay. Hydrogen, 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 hydrogen. Okay, hydrogen has to be with opposite spin. So it will be pointing down here, but there, because carbon has a spin that pointing down, I'm going to show this one up. Okay, again, it doesn't matter. Okay, just keep them opposite. Okay, keep them opposite of each other. So now we got a sigma. That's another sigma, sigma here, and that's another sigma. But carbon, any carbon that you pick is not octet, okay, is not octet. So what's the solution for it? Okay, the solution for it is, okay, until now, you got carbon attached to another carbon, and you have 2 hydrogens on each carbon. And time to introduce the pi bond. And that's going to be plus, plus, okay. This one will be minus, minus. And remember, you have 1 electron in each of this orbital. Okay. And you're going to have interaction between them. And again, the second carbon, okay, second carbon, it has the spin that is pointing down. So you want to be more accurate, show this one pointing down, and that one is up, and they will have interaction. And that interaction is going to give you a pi bond technically. That's responsible for the double bond. Okay, so each carbon, it has 3 sigma bonds. It will get through the 3 sigma bond, it will get 6 electrons, 6 electrons for 3 sigma plus 2 electrons for a pi bond. And that's going to be equal to 8 electrons, and it will make carbon octet. Okay. Again, okay, we're going to switch to another bit sophisticated system. Okay, so I showed you the orbitals, like we have a 3 sigma bond, okay, and a 3 sigma bond for each carbon and 1 pi bond to make carbon octet. Again, the pi bond, it has a node, okay, And as you see here, it says negative, and so like a blue, sorry, the red. So you can call this one plus, you can call it, say, plus, plus, but here it will be minus, minus. Okay, where is the node? This is the node. The surface on the plane, it will be the node. Okay, now we're gonna go and check it through molecular orbital theory. And as you see, the molecular orbital theory is showing us that two p orbitals reaching each other. Okay, each p orbital has one electron. One is pointing up, and the second one is pointing down. So be careful about this. Up, and that one is pointing down. And now you pair them, and you get one pi bond. Okay, we got one bond. Okay, we call it pi bond. But that pi bond, it has a node. How do I know it has a node? Because the top it says red, and we can call it positive, and this one is negative. The color is different. So clearly pi bond has one node. How about the pi star orbital or anti-bonding orbital? That one clear that has two nodes. One node is here, and the second node is going to be there. Okay, so it's a phase from positive is turning to negative, and negative turning to positive, and then negative. So we do have two nodes. Okay, again, let's make it a bit more complicated and introduce the second pi bond. So the example that we're going to talk about it will be this. So we had C2H4. Last example, we're going to subtract another two hydrogen from it. And this one, it will give us C2H2. Okay, C2H2. And you will have a carbon attached to one hydrogen, and that carbon is going to attach to another hydrogen. Okay, now is carbon acted? Clearly carbon is not acted. Carbon, and it has, if I draw a circle around carbon, any carbon, I see two electrons here. So I'm going to say two electrons plus, we made one sigma, another sigma here, another plus two more electrons, and that's going to be equal to 4. So carbon is not acted. Carbon is missing 4 more electrons to be acted. How can I make carbon acted? Let's introduce pi bond to make it acted. Okay, so carbon is going to have triple bond, okay, to reach acted. This is going to be sigma, sigma, sigma. Okay, let's highlight one of this carbon and talk about the hybridization. So for carbon, we have 2 sigma bond. Again, we have 2 pi's. I don't care about the pi. This is pi, and that one also is pi bond. Pi bonds, we'll get them after we're done with the hybridization. So that's the reason I said I don't care about it. Okay, so I say this. I say I have 1 from S, 3 from P, and 5 from D. How many orbitals do I need to accommodate those 4 electrons? Remember, we had 2 sigma bond, 2 multiply 2, because we use 2 electrons per each bond. So totally we have 4 electrons. So I'm going to say I have totally 2, I need totally 2 orbitals. So I go 2, and then I use 1 from S plus, I need just 1 from P, 1 from P. 1 plus 1, that's going to give me 2. Okay, and I get S and P. What's the contribution of S? 1. How about P? Again, 1. So this one is 50% S character, 50% S character, and 50% P character. Okay, next. Okay, let's show the hybridization for each carbon. Okay, so we have a carbon that it has 2 hybrid orbitals. Each carbon has 2 hybrid orbitals. Okay, we're going to put 1 hybrid orbital here. Another hybrid orbital, we're going to put it there. Okay, I can copy paste this or write the second carbon here. This is the second carbon. So that's going to be another hybrid orbital. Okay. Okay, so carbon is group 4. Means has 4 valence electrons. Let's show the valence electrons for one carbon. So this one is going to be up, and here it will be up. Okay, and what else? And the second carbon, in order to have in sigma interaction, we need to put the spin pointing down. That one, of course, is going to be pointing down. Okay, now those two carbon, they will reach each other, and that's going to give you sigma interaction. Okay, and this is the first sigma bond. Okay, what are the hydrogens? We're going to put the hydrogens here. One, and that's going to be the second hydrogen. Let me use the same color for both of them. Hydrogen, hydrogen. Okay, hydrogen, it will have opposite spin. Okay, again, we got sigma bond, and that's going to be another sigma bond. But carbon is not active. Any carbon that you pick is not active. But the hybridization, it clearly is sp2. Why sp2? Because I need to have one, sorry, sp, forgive me, not sp2. One hybrid orbital here, another hybrid orbital there to make 2 sigma bonds. Okay, to make 2 sigma bonds. Now, what's the bond angle? The bond angle from hydrogen to the second carbon, it will be 180. Okay, but carbon is not active. Okay, carbon is not active. And carbon right now has this geometry. Okay, in order to make it active, we're going to put one p orbital here. I think I need more space, so let me write it in a different page. Okay, so I'm going to draw one p orbital here. And I say this spin, it will be pointing up, down. Okay, this one is a plus, plus, minus, minus. So what do I get? I get 1 pi bond. I get 1 pi bond. Okay, so now carbon, any carbon that you pick is sensing, okay, technically 2 sigma bonds plus 2, 4, and 1 pi bond also we have. So carbon is sensing 6 electrons. We need one more bond. Call this one P, for example, PZ, PZ. Okay. And carbon, right now, it has, say, H, sorry, the hydrogen attached to carbon, and attached to another carbon, attached to another hydrogen. In the previous step, you already made 1 pi bond. Let's show it. Okay, so carbon still is missing 1 bond to be active. And that one, you can get it through this pi interaction. You have another pi bond, another p orbital inside the plane that we did not use it. Why? Because carbon, it has 4 valence electrons. I go back. For making 2 sigma bond, you already used only you use only 2 electrons out of 4. And the third electron, you use it here to make 1 pi bond. Okay. Now, where is the 4th electron? The 4th electron on each carbon, it will be here, pointing up. So say this one, again, pointing down. This one is pointing up, plus, plus, and that one is minus, minus. Now I'm going to get interaction between those p orbital. And that's going to give me carbon attached to another carbon through a triple bond. Okay. And what's the bond angle between hydrogen, carbon, and another carbon? I'm talking about this bond angle. theta, it will be around 180. Okay. And okay, so I think I'm going to stop the lecture here. Okay, thank you very much. And I hope this lecture was useful to go a bit more in deep about hybridization.